Imagine a complex machine running for years without a hitch. Then, a single drop of oil lands in the wrong gear, initiating total collapse. In the aftermath of a crisis, our intuition searches for a direct line from cause to effect. We hunt for a specific trigger or an external enemy to blame. We might point to a political leader for a failing economy, or blame a new competitor for a sudden loss in market share. Systems scientist Donella Meadows recognized this pattern of diagnosis in the daily news cycles of the early 1990s. Headlines presented isolated crises, like the retreating Iraqi army setting Kuwait's oil fields ablaze. In the same window of time, Nelson Mandela walked free from prison, and South Africa dismantled the laws of apartheid. Simultaneously, major trade treaties like NAFTA were signed into law, celebrated as distinct political victories. These stories appear as disconnected events triggered by specific actors. In reality, they reveal the massive underlying system structures shifting all at once. Operations theorists call these situations messes, evolving webs where problems are trapped in a dynamic, interacting network. Targeted technical fixes often fail to eradicate chronic issues. Issues like widespread global hunger, the epidemic of drug addiction, and severe environmental degradation persist even when we direct our best analytical efforts at them. These undesirable behaviors live within the internal structure. The system itself produces the crisis. The external event simply triggers it. Addressing the world's most persistent failures requires looking past external symptoms to identify the internal logic generating the errors. The bounce lives in the coils of a slinky. When a hand lets go, it simply releases a behavior already latent within the object structure. A system requires three specific parameters: a set of elements, interconnections holding them together, and a coherent function or purpose. This diagram shows how raw elements rely on invisible interconnections. In a university, the buildings and students are elements, but the rules and academic standards are the interconnections that drive the outcome. When those interconnections vanish, the system ceases to exist. It becomes a mere conglomeration of parts, no different than sand scattered on a road. Because of this internal organization, any outside event applied to a system will unleash a behavior characteristic of that system's design. Dissecting the individual elements alone leaves us blind to the rules of the game that actually determine how the system will act. This visualization represents the feedback loop, the engine of system behavior. These loops determine how the structure processes inputs over time. A reinforcing loop rewards winners with the resources to win further competitions. It leads to runaway growth or sudden cascading crashes. A balancing loop seeks goals and maintains equilibrium. It absorbs outside shocks to help a system return to a baseline state and mend itself. Complex systems also contain latency. Delays in these loops mean the consequences of an action are rarely immediate, obscuring the link between a choice and its result. These hidden mechanics explain why actions that have worked for years can suddenly fail, and why systems can jump into entirely new patterns of behavior without warning. In a Sufi story, blind men try to identify an elephant by touching its isolated parts. One feels the leg and assumes it is a pillar. Another feels the trunk and assumes it is a pipe. Modern analytical training often forces us into this same trap, tracing direct paths from cause to effect while isolating small, understandable pieces. We must view these integrated architectures holistically, seeing how their internal parts maintain the whole. Recognizing the system as the source of its own problems allows us to move from reacting to external events to actively intervening in the system's design. Identifying the internal architecture helps us find leverage points, specific places where a minor structural shift produces highly desirable behavior across the entire network. While we cannot forcefully control the world's complex messes, identifying the systems driving them is the first step toward redesigning them for a better future.